Welcome back to 5-Minute Chemistry. Today we are finally going to be talking about the real mass of a single atom. Since Dalton, the mass of the atoms was a point of interest for chemists, and now that we know what atoms are actually made up of, we can know their actual masses. So we have the concept of atomic mass, which is defined as a single atom's mass. So it is M with an A in the bottom right index over there. So this is going to be used to measure the mass of a single atom in the unit of Dalton, or U, or sometimes it's written as AMU, like atomic mass unit. But these are the same units with different names. And this is defined as the mass of the carbon atom, which has 6 neutrons, 6 protons, and 6 electrons. So its mass number is 12. Is defined as exactly 12 Dalton. So this is not a measurement value. This is the definition of the unit of the atomic mass Dalton as 12 for the carbon-12 nucleides. This is not going to be the same as the mass number. For carbon-12, it is the same because we defined it to be the same. But actually for other atoms, the atomic mass will be different than the mass number. So you cannot just add up the number of protons and neutrons and know the atomic mass, because relativistic effects will change that. So actually the mass of protons and neutrons will be different from atom to atom because of the high energies that are involved in bonding the nucleus. So the other concept which we already talked about is the relative atomic mass. Relative atomic mass was used to describe the masses of the atoms relative to each other back at the time when the actual composition, the actual size of the atoms was unknown. So this goes back to Dalton's atomic theory. But what we found out is that actually not all atoms of an element are the same mass. So we cannot just use one element as a reference, which back then they just used hydrogen because that was the atom with the smallest mass, so they just try to use the atom of the element hydrogen to be the reference. But now we know that instead of an atom, we actually select a nuclide as a reference. So, well, a nuclide is an atom, but it's defined not by just what element it belongs to, but also how many neutrons it has. So luckily here, the standard reference is the same as for atomic mass, which is the carbon-12 nuclide, which is now 12 times the atomic mass constant. So here the atomic mass constant is used as like a quasi-unit, but relative atomic mass, because it's relative, it's in the name that it's relative, it is generally unitless, but because the definition is based on the same thing as from atomic mass, the numbers should be the same. So we can, basically for an element, we can get the relative atomic mass for the specific element by having a weighted average of the mass of the atoms that it's made up of. So if you have a sample and you know how many of the carbon atoms are carbon-12, how many of the carbon atoms are carbon-13, etc., you can make like a weighted average to get the relative atomic mass for the carbon element in your sample. So this thing is standardized to be the standard atomic weight. For some reason here, still the word weight is used instead of just saying standard atomic mass. But the standard atomic weight is just basically the relative atomic mass, but the sample is defined for the whole Earth. But of course, we cannot just go around and measure all the carbon atoms in the whole planet to get a value. It is based on various samples, and these values are collected and then published by the International Union for Pure and Applied Chemistry. For some elements, there is variance between samples that is also usually published with these documents. So let's try to keep our concepts clear, because the standard atomic weight is something that you usually see in your periodic table below the names or somewhere around that area. But let's keep in mind that here it does not mean that we are talking about the nitrogen-14 nuclide or the bromine-80 nuclides. So the mass number is always for one specific nuclide, while the standard atomic weight is for the whole element. So all of the nuclides that make up this element are averaged into this standard atomic weight. So if we talk about the bromine specifically, bromine actually does not have a naturally occurring isotope with 80 mass number. So even though its standard atomic weight is around 80, bromine is mostly made up of 81 and 79 mass number bromine atoms. So to get the standard atomic weight here, we actually just multiply the abundance, and this is going to be a percentage that is for the whole planet Earth, because we are talking about the standard atomic weight. So the abundance of the 79 mass number nuclide is multiplied by the atomic mass of the 79 nuclide. And you can see here that the atomic mass for the nuclide with the 79 mass number is actually smaller than 79, 78.92. So there is also different, but then you just add up the abundance times atomic mass for all the nuclides, and then because it's in percentage, you divide by 100%. And so here, this is how you get relative atomic weight for bromine around 80 without actually having bromine 80 nuclides in the sample. Just keep in mind that these four concepts are different. So mass number is just the number of protons plus neutrons. Atomic mass is the mass of a single atom, and it is different for each nuclide, of course. Relative atomic mass is defined for the element in a certain sample, while standard atomic weight is defined for the element for the whole Earth. So this is it for today, and I will see you tomorrow.